All right, so last week we were looking at the image inputs. Um, we flattened them and then we passed them through a dense neural network and we trained it and we saw, oh, it's pretty impressive. We can actually recognize airplane versus bird reasonably well. Didn't do amazing on unseen data. It could figure out the training data, but then it only did so-so on the validation data. It was doing slightly better than just a 50-50 split that we would have expected. And so in this chapter, we're looking at convolutions, which is what gets us kind of over that hurdle and helps us generalize a little bit better. It's been kind of one of the big revelations in deep learning is convolutional neural networks have really transformed the way we handle images. And so this chapter, we were looking at convolutions and understanding what is that operation? How do we build a neural network out of that operation? And so the big advantage for convolutions is we're able to capture local patterns. So later in the chapter, they talked a little bit about you have those 3x3 kernels or 5x5 or whatever size your kernel is. And so it's looking at that local pattern, just a small set of pixels, and it has an understanding of what is close around it. Whereas in the flat dense neural network that we were looking at, it just assumes everything is fully connected. It doesn't really have an understanding of which pixels are close to each other and what relationship is happening there. And then it also introduces the property of translational invariance, where previously we were just memorizing the pixels over here are slightly brown and it's got this shape, and so that means it's a dog. And then if we push that same pattern to the right side of the image, all of a sudden it doesn't know it's a dog anymore because it only memorized these specific pixels need to fit this kind of condition. And so doing the convolutional operation allows us to recognize a pattern anywhere in the image rather than just memorizing specific locations and intensities. And so the gist of the convolution, see I've got an extra character there, is you've got those kernels that I was talking about, and you slide those across the image and you do a linear combination of those kernels. So for example, probably easiest if I just pull up the diagram that they had. So basically imagine that we have this 4x4 image and then we've got a little 2x2 kernel. And so we would apply it across, actually that's the max pooling picture. Let me find the original convolutional one. So let's say we have this 4x4 image, yeah. And then we have this 3x3 kernel and we're applying it across the image. And so we take one snapshot that's here, and then we see that we're multiplying these and then summing them. And so we see that the zeros match with the ones, and we've got 5 1, so we end up with the 5 output here. And then we slide the kernel one to the right, and then we get a different amount of overlap. So we only have the overlap of this one and this one, so we end up with 2. And then we push the kernel down 1 and back to the left side, and then we do that again. And so we end up with 5 and 2 and 2. So does everyone understand that convolutional operation, or are there any questions in that regard? So if not, we'll move on. And so in the second section of the chapter we were looking at, you can do all kinds of different convolutions. You can do it with a 1D kernel, a 2D kernel, 3D kernel, etc. You can keep going to higher dimensions and then apply it to different kinds of data. So for example, I'm working on some stuff with video, so it might be appropriate, since we have the additional dimension of frames of data, you might want 3D convolutions instead of 2D convolutions because we have that time dimension. And so it's kind of important mostly to know the 2D convolutions because that's what most people use. It's not that common that you go 3D and beyond. And so understanding the 2D convolution operation we're building a kernel, and it's not just a 3 by 3, because typically you have multiple channels. So you have your red, green, blue. So that's 3 input channels, and then you might have several output channels. And so you're doing the linear combination of these 3 channels, applying a 3 by 3 convolution, and that is then outputting 16 channels, because you're taking those 3 channels and distributing it across 16 different channels. And so what that actually looks like in practice is, let's say you have your red, green, blue image, you apply that kernel to it, and then on the output, now you have 16 images, a single image that is 16 channels now instead of 3 channels. So just something to notice, because you'll look at the convolution layers in your network, and it'll output and it'll say the kernel is 3 by 16 by 3 by 3, and you have to understand, okay, it's not just 3 by 3, it's actually a matrix of this size in order to do this mapping. And so, like what I was saying, is you might have an image that's 3 by 224 by 224, and then you're mapping it to 16 by 222 by 222. And it ends up slightly smaller on this dimension because we might not have padding. And so one of the things they talked about is, if you have a 3 by 3 kernel, you're sliding it across the image. You have one option, which is, I'm only going to apply it to the pixels that I actually have. But then that means that because you're doing this reduction, you're going to end up with slightly less pixels on the height and the width. Or you can pad it, which is you put zeros or you put something else on the periphery of the image, and then you make it maintain the original resolution that it started with. And there's various different arguments as to why you would want padding or not. So
anybody has practice, with it? Is padding helpful or not? Because I tried it once. I tried to remove it once, and it was better. And it was image recognition.
Mm-hmm. It depends on the task that you're doing. I think is the biggest differentiator there, because one of the things they mentioned was, like, in a UNet or something like that, you're specifically trying to locate things within the image, and when you're doing that reduction, you're losing precision the whole time. And if you have to map that back to, let's say you do a 224 by 224 image, and you want to map where in the image is the thing that I'm interested in, and every convolution you're losing a little bit of precision, then it's actually useful to have things lined up. So you add the padding, and then it makes it so your output can still be 224 by 224, and matches exactly to the input image and the mask that you're trying to predict. And that's true of object recognition, and segmentation, and the various varieties of that. But in practice, I don't think that padding typically makes much performance difference if you're just doing like CFAR10 and ImageNet and stuff like that.
Hey, Ryan, if I could just kind of pause and reiterate a point, because I've seen convolution before, and I understood the general concept, but I never really worked out the nitty-gritty details. And then reading this chapter, I got really clear. So if you have a standard color image and it comes in with 3 channels, okay? And let's say I have a 3 by 3 filter, and let's say it's, one of the classic ones, like it detects vertical lines, okay? In reality, that filter isn't just 3 by 3, it's 3 by 3 times the number of channels. So it could be detecting vertical lines in the red channel, but doing something completely different in the blue channel and something completely different in the green channel, right?
Mm-hmm. Yeah.
Because I've always very simplistically thought about, like, oh, if you're detecting vertical lines, you're just going to do that on all the channels. But by no means does it have to do the same thing on all the channels. And then further down, I guess you expressly don't want it to do the same thing, because now if you have whatever 64 nodes in your first layer, those 64 channels are potentially encoding very different things. And so you're not going to do, you might want 2 eyes and 1 nose. And so you don't want to do the same thing on each of those. If you had an eye finder and a nose finder, you want different properties when you're looking at them, right?
Yeah.
So I don't know if everybody else just got that a whole lot faster than I did, but I just wanted to say something because it actually has taken me a while to really deeply understand that that's what's happening.
So Ted, question for you. Are you assuming that the filter on each, or the convolution, I should say, on each of the 3 channels for the RGB, for example, are different or the same?
Yeah, that's my point, is that all of the book examples are typically for a single channel image. And so they just show you like, hey, look, here's a 3x3 or a 5x5. But in reality, when you say, I have a node in my CNN, that each node, each filter is not only whatever you say, 3x3, 5x5, it's also as many channels deep.
Yeah,
so,
I get that. Yep. But
yeah.
I think what I'm pointing at is I had made an assumption, right? So in the book, for example, he uses a cross, right? He just uses a as the convolution, as the filter, right?
Right.
I had assumed that he was using a cross on all 3 channels, but in theory, if you set up a filter and you randomly initialize each one of them, the R channel can get one configuration, let's say a cross, but then the G channel maybe gets a circle and the B, channel gets a square or something, right?
Yeah, it seems unlikely to me with random initialization that you would get like, hey, look, here's a node where all 3 channels are doing vertical lines, and here's another node where all 3 channels are doing horizontal lines. Someone somewhere may be doing, vertical lines on each channel, but yeah, it's not going to be quite as clean as conceptually I thought of it that way, but it only upon reading this chapter that I realize in actuality it's a little bit messier. It's not, it's not like there's some top-down God who just sort of says, okay, you do circles, you do vertical lines, you do,
Okay, good point. Thank you.
But that makes sense too, because I was actually thinking about 3D images with 1 channel, which, that's like however many channels down, which is a different section of that, like CT scans. So that makes more sense to me now why you can pick out, or even time videos, let's say, right, where the depth dimension is time. That makes a little bit more sense now why the different channels can pick out these different features, because they're all randomly initialized, as opposed to all being, vertical line filters. So thank you for the clarification, Stephen and Ted.
Yeah, so one of the things Ted mentioned was the sort of classical filters. And so a long time ago, people kind of discovered that the convolutional operation was useful, and they also kind of hand-derived various different filters and kernels that they found to be beneficial for certain things. So an example of one of them is the Sobel operator, and basically they figured out, like on the last one we saw a cross, and that's just a simple pattern that you can apply, but they also figured out that you can do this specific configuration of a 3x3, and then it will actually be useful for finding edges in images. So you can take something like this and you turn it into something like this, because it's able to capture vertical and horizontal lines and differences in intensity pretty well. And there's a lot of different examples of these that people found out over time. And so these work pretty good for very specific defined things, but then a lot of the time with these networks, we're trying to figure out some arbitrary thing like a cancer cell or a cat or a dog or something like that that isn't as well defined as just a vertical or horizontal line. And we need to be able to derive that rather than kind of inject our own knowledge into it. And so the beauty of the CNNs is that we're able to automatically find these filters rather than just defining them by hand. So one of the issues with these 3x3, 5x5 filters, are kind of the standard ones that most people use, is that you look at that, and if you only have vision of a 3x3 region, you can't really tell very large patterns. And so in order to expand upon that, you can do a whole bunch of convolutions, but then that ends up being pretty expensive. And in turn, what people have figured out is you can do pooling layers. And what the pooling layers do is it will take some certain region and it will take either the average or the max or some other operation over that region, and then you can reduce the size of the image, and it increases what most people call the receptive field of your convolutions. So if you have that 224 by 224 image, you apply a convolution on it, and you end up with 222, and then you might do 2x2 max pooling. So you look at 2x2 regions across the entire image, and you take the max of that, then you end up with half the size of that image, which means that your receptive field on the next layer has doubled, essentially, at the cost of a little bit of precision, potentially. And I started working on a notebook to show that concept a little bit. It's not necessarily done, but we can peek at that a little bit later. So the two key things that I think we should pull here is the convolution operation and the max pooling, average pooling operation. Those are the two things that you really need to know about, and looking at the actual networks and then trying to apply the operations one at a time can give you a pretty good intuition of understanding, okay, I've got this image, I apply a convolution on it, now the output size is this, then I apply max pooling, and then the output size is this, and you can kind of follow it along and understand, okay, what exactly is happening with this.
I had a PyTorch question. So for the max pooling layer, is the default stride to always match the kernel size? So I wasn't understanding the output at first, and then I realized that's what it was doing. So
I believe so. I'd have to look at what the actual documentation says, but I believe so. If you put kernel size of 2, then I believe it'll make the stride 2. We can look at that in a second, though. What did you say, Hobbs?
I just assumed the stride was always 1 by default.
Yeah, I mean,
I'd
we're
say
talking
its
about
default is
like
kernel size.
well, so when I was
No,
looking at it,
even in
okay.
Keras it is variable.
You're right.
Yeah, so it says
Right.
default value is kernel size. Yeah. And so what they were showing is we can do all these operations, and then at the end, what we need to do is some sort of reshaping function. And unfortunately, it doesn't work out very elegantly in the nn.sequential format. And so that's when they started introducing subclassing the nn module, which is the way most people define neural networks in PyTorch now. Sequential is nice if you have some simple layout, but most of the time people have stuff that's a little bit more complicated than that. So moving on to the next section, subclassing the NN module.
The one thing I found that I couldn't do with the sequential model was the dot view. So I couldn't change the shape of something and pass it from like a CNN into a linear layer or whatever. Mm-hmm. Interfacing different kinds of layers with each other, you often need to use a view.
Yeah. And so the two things that you need to have a valid model is you need an init and you need a forward. And so those two things, the way that I think of them is one of them is initializing the layers of the network. And then the forward pass is saying, how do I actually connect all of those together in order to do the operations that I want and get the output that I want? And so, yeah, just went over that. And so it gives us more freedom in that we can do all kinds of different branching paths. You can even do crazy stuff where you say, if the output of here is beyond a mean of this value, then go down this other network path and stuff like that. You can do all kinds of crazy stuff with PyTorch that you can't necessarily do in Keras. You can do it in TensorFlow somewhat, but not necessarily in Keras with that wrapper on top of it. And so that gives us a lot of flexibility. We can do all kinds of different things. And one of the, go ahead.
Oh, no, sorry. If you continue, I'll ask it after.
Yeah. So one of the things that I thought was interesting was they noted that famous practitioners also go through and they just kind of plug the numbers in to figure it out. That's my process too, is sometimes I go, okay, I don't know the exact calculation of this padding and then this convolution and then this max pooling. What's the output size of that? You can theoretically capture it all by hand and say, okay, I need to do this equation to figure out what the next size is going to be. But typically what I do is I just kind of plug it in and I say, okay, does this work? Is this what I expect? And they're saying that even famous practitioners do that. So that was a little bit soothing to understand that I'm as much practice as I've gotten, that's still kind of the way that people operate and do things.
So my question kind of went, they have the differences between, like you said, building the class and then implementing the functional API where you use the functional.max pooling. And I wasn't sure the benefit besides like minimizing the amount of lines, I guess, you have in your code. Is there, because I actually felt the non-functional API was easier to read, at least following it, how it went down the path. And maybe that's because I'm coming from a Keras perspective, but I was just kind of curious about that.
I don't know that there's really that much difference there. The big thing is that I really don't know that there's much difference there, because in one path you're saying I'm going to define a max pooling layer and I have a different max pooling layer for every single time that I apply it. And it's not entirely necessary because you can just do the functional and you're doing the same thing no matter what. There's no learnable parameters. There's no anything going on. So you might as well just use the functional because you just say, I'm going to apply this operation. I don't necessarily need a layer defined for this specific thing. But I don't know, maybe there is some implementational difference that I'm not aware of.
So I got the impression that there was a computational advantage in using the functional. Did I get the wrong impression?
I'm not sure that there is. I'd have to look at it more closely. I don't know that there's any real difference between the two.
Okay.
I think the authors mentioned, at the end of the day, right, it's building a computation graph. And so I'm assuming that that is optimized enough that you're going to get identical performance, basically identical code either way. It occurs to me that as someone who's not an object-oriented programmer, like having less code in the init makes me happier, because I don't really like the idea of writing init functions. But I'm not sure if you go with their, not the original one where they just have a layer type for each thing, for the activation, for the max pooling, whatever. If you actually use those as functions, then if you were doing something like print out a summary of all the layers, I'm assuming they wouldn't show up anymore, right? You would just see convolution, convolution, convolution. It wouldn't tell you what the activation, what the max pooling that happened in between was.
I believe that they would still show up. My understanding is they would. I can actually check that because I have a network that's running on my desktop right now. And I'm pretty sure it still shows up because I think that's defined by the forward pass. And so if you know that, so what I was doing is you have the max pooling layer and you just say, I'm going to define it once and then apply it 8 times. I believe it still shows up in the network graph. And I think it's because it's found by doing a forward pass. I'm not sure.
Okay.
I'd have to
I mean, basically, it's a print function, so they can decide what they want to print. They say, well, we'll also print, you know, functions and other things too.
Yeah.
But I don't know if that answered your question, Tommy.
No, yeah, I wasn't sure, like, I think what Anne was going with it. Is there any other benefit besides reducing the number of lines? So it sounds like it doesn't, but, you know, to your guys' points, it might be more easier to do it the way it's done with the functional API reading wise. So I understand that.
Yeah. Yeah, and also even just the fact that they put like 3 things on one line of code, right? They said like max pool of, you know, ReLU of conv2d, right? So there's 3 things, whether you think of that as 2 layers or 3 layers, 2 layers in an activation or 3 layers, like there's clearly 3 things on one line, and you know, it's reasonably readable in my opinion. It's reasonably short line, so it's okay, but definitely from a beginner first time reading it through, it's like you took a whatever 12, you know, layer network and you wrote it in 5 lines of code. So it's not, as a beginner, to me, it wasn't instantly obvious. I had to kind of do a double take and say, oh, look, there's 3 things on one line.
Yeah.
Well, that brings up a whole other discussion around how maintainable code is, right? So if you have to hand this off to somebody else who's never seen it before, or even worse, you come back 6 months later and you've forgotten everything, right? Which one is easier for you to read and get back up to speed on?
Yeah, I think that's a potential separate debate.
Oh, absolutely.
But you know, if one wanted, you could have a convention where you just do 1 line of code per layer, even when you're using this, you know, subclassing API.
I think in general, I think it is always good to write the best code that you can and try and organize it in a way that's readable later. But in general, when I've looked at these models, even a complicated one is going to end up being 100 or 200 lines maximum, really. Because there's really, like, you can't go beyond a certain length because we just don't have the compute capacity to do 100 layers, typically. So it's important, but I would say it's not something that I run into that often, that I look at a model and I say, I just can't follow this at all. And I've looked at lots of people write models. So I don't know. I think it's somewhat intuitive after you look at several models that they mostly all look fairly the same, even if they might stack multiple things on a single line.
Yeah, from my experience, you know, this is all a balancing act, and you know, you have to have your task of what you're trying to do, and then you have your images that are coming in, and then what the accuracy is versus the performance, and all of this is just a balancing act. And in my case, everything is performance. I want just the best accuracy, but the highest performance, and so we have to tailor each one of these layers very, very discreetly, because these massive neural nets, they actually, in the stuff that I'm working on, they don't actually perform all that much better, but they're much slower. So yeah.
Yeah. So moving on to the actual training process, we've been using the same training loop template every single week, and that's kind of what I posed early on. Is when we first did it, it looked kind of complicated, but we realize now every project you're basically going to use a similar loop where you're saying, okay, I need to compute the loss and make predictions and do the backward pass on the gradients. And so it's kind of something simple that you can just copy paste for every project you're doing. And we're doing the same thing here. We're just adding a couple additional layers. So in this one, they built on top of it and they said, let's add some validation process, because we're trying to present this to someone and they're not interested in what the loss value is. They're interested in the accuracy of our model. And so they add a validation process where we're making predictions on some unseen data, and then we're taking the max to figure out, okay, which class do we actually predict? Are are we correct? Are we incorrect? And then you can measure the accuracy with that and get an actual value to report on that. And so we add that in, we train a model, we see the model performance looks pretty good. It's significantly better than the fully connected network. And so that's a good step forward. We have less overfitting, we have better generalization. And so that's the power of the convolutional neural network. And then after that, they show how we save. And so that was one of the tricky things for me with PyTorch when I was first starting off, is the typical recommended way to save is just to save the state dict. And so what the state dict does is it has the names of the layers and then the weights, the arrays that go along with it. So you'll have your first conv1 layer, and then all of the weights that are assigned with it, and then your conv2 and all of the weights that are assigned to it. And so after that, then you take your weights, and if you want to reload them in again, you need to actually define the shape of your network in exactly the same way again, and then load in the state dict and say, assign all of these layers to have these weights. And so that's a little bit different than Keras. In Keras, you just hit save and you just say, okay, next time I want to load this, load the model, and it brings along the optimizer and the model definition and the states and all of that other stuff. So just a small difference in the PyTorch implementation that you need to kind of be aware of, because you might want to actually deploy this model somewhere and you have to realize that you also probably want to bring along the model definition code. So if you're experimenting, you want to keep all of the different versions that you have as you're going.
Ryan, have you seen, is there any standard way that people are actually saving their model architecture to files? I mean, you could just pickle it, but is there something like Onyx or something that's gathering any momentum that you've seen?
Not necessarily. That's something I've been looking into, because I've been working on the lift competition, and I train a model and then I put it on Kaggle and then I do predictions on Kaggle. And I've been trying to figure out, how do I actually like transport the weights and the code and keep those bundled together and everything. And I haven't quite figured out a good series of operations for that. I'm sure there's some better way than what I'm doing right now, but I haven't figured that out yet. So I'll have to report back some later time.
All right, maybe you can just have sort of a tuple of the model and model weights, right? And then just manually pickle it instead of using the built-in save model function. Yeah. And then at least they're together in the same file so that you can't accidentally mismatch them.
Yeah, that's definitely possible. There's a lot of different ways that can be done. I just need to do my homework and figure out, because I'm sure there's some better recommended way to do it. It might even be what you described. But I assume that the torch.save function exists for a reason. So I need to figure out the corresponding piece that goes for saving the model definition as well.
Yeah, and I will just comment that, like, I tend to have a lot of models that do have the same number of weights. Like I may be changing, like changing dropout levels, changing some of the math and some of the normalization and things like that. And so it doesn't change the architecture. And so I could actually load the wrong weights and not even realize it. So that scares me a little.
Yeah. So one of the last things they showed in that section was moving on to these convolutions. They're actually more efficient than doing the fully connected dense layers, but they're still fairly slow. And so one of the advantages of the convolutions is they can be easily parallelized. So if you think about it, we have the kernel. You can apply that kernel in all of the different locations all at once rather than one at a time. And there's no real relationship there. You can just do them all in parallel separately. So when you have a GPU and it has all of these cores, you can just distribute the work out, and you can say do all of these all at once rather than doing it one at a time sequentially. And so you can make the convolution operation way, way, way faster than if you were doing it on CPU. And so during the training process, you probably want to push to GPU, and it's fairly simple to do that. If you're just pushing to a single GPU, then you can just do .2 and then CUDA, and as long as you have a GPU and you've got CUDA installed and all of that set up, then it just pushes it to GPU, and then you're able to compute a lot faster. And so the two things you need there is you need to push the data to the GPU, and you also have to push the model. So they're existing on the same spot, so you can do that operation. If you want to do multiple GPUs, it's actually not very hard either. There's this data distributed layer that you just wrap around your model, and then what it will do is it will send half of the batch to one GPU, half of the batch to another GPU, or more if you have more GPUs. And so it's not very hard if you want to scale up even further. And then if you want to go beyond that, there's, I don't know exactly what it stands for, but there's like DDP or something like that, and it allows you to do even greater parallelization, so you can go across systems rather than just across GPUs in a single system. But most people probably won't encounter that. I haven't had any reason to come across that.
Hey Ryan, can I make two quick comments?
Yeah.
So one is, I remember the first time somebody was showing me convolutions, they commented that like a lot of Photoshop filters like sharpen or blur are just, you know, convolutions. And so, so it's actually not surprising at all that graphics cards would have really good support, fast computation for matrix multiplication and convolutions, because you do a lot of that in graphics already anyway, right? Before even, right, deep learning became a thing, right? But the other comment I wanted to make is that the reverse of, if something's so big and you want to spread it out over multiple GPUs, the reverse is also true. It's a pain in the neck to have multiple Jupyter notebooks open and be running small little Keras learning projects that don't use up all of your GPU memory. It's a pain in the neck to try to do that with TensorFlow. And thankfully, it's actually much easier with PyTorch because PyTorch won't just hog up all the memory on your GPU in one fell swoop. And so if you're just doing little projects, as again, because you're learning, not because you're really training some, you can have multiple notebooks open, and it's much nicer.
Yeah. So in Keras, it will automatically grab all of the memory it can, whereas in PyTorch, it will just allocate it on the fly as it needs it. And so that it's a blessing and a curse, because you can end up with something where all of a sudden it hits the correct like overlap, where all of a sudden you overflow your memory if you have multiple experiments going on. But at the same time, it gives you that flexibility, so you can do something like that if you want, as long as you're conscious and careful.
Yeah, and I think there is somewhere a command in PyTorch where you can say, go grab this memory, and then you make sure that it's there when you want it later. If like it's going to take half an hour before you actually, you know, get to allocating all of it, you can just say, grab me this much now, hypothetically. But you can also give back memory, which you can't do in TensorFlow. Yeah. So once you've used, you know, 8 gig, then the only way to get it back, that I mean, I've looked at like Stack Overflow and stuff, and everybody says, no, the only way to do it is you basically have to kill your session and completely remove all of the links to that TensorFlow, and then Python will basically be gone, and all the memory will come back.
Yeah. So in PyTorch, that option that you were just mentioning is the pin memory option, in case anyone's curious. I haven't seen any great benefit to it. They do mention in the documentation there might be some scenario where you get a performance boost from having the memory pinned, but I I haven't used it that often, but I also have tried it a few times and it's never been beneficial for me. So your mileage might vary.
Is there, so speaking of the two function with the transfer of memory, is there a way to load the training data by default into GPU memory? Because as part of the model definition, they have that section where, you know, you have the train loader, which then takes the image and then transfers it to memory with all the batches, and then you do your processing. And I imagine that takes some time to do that as opposed to just loading it to GPU memory directly. So I was curious about that.
I'm not sure on the details of that. I haven't typically run into a bottleneck in that regard. So almost every scenario that I've seen has shown people doing it. So their data loader pulls the data, and then after that they put to CUDA, and then they do the operations. And I think you kind of have to, because GPUs don't actually have that much memory. And when they're doing the convolutions and all the other operations, they have to keep the intermediate steps and the gradients and all of that stuff. So they use up the memory fairly quickly. So you don't typically have the luxury of being able to say, I'm going to put all of the data on GPU memory. You have to do that transfer at some point. But luckily, the memory to GPU time, you have very high bandwidth, so you don't actually run into that big of a bottleneck there.
Yeah, I think that's right, that's the common use case. And so let's say you're doing like image augmentation. You can do that on your CPU and then just copy it over to GPU, you know, and usually there's enough CPU horsepower to just keep up so that you're pipelining stuff into GPU. But Ryan, I thought I saw NVIDIA said that they are building a library driver, whatever, which would allow direct access straight to the GPU. Mm-hmm. So that you literally could say, open this file, and when you pull whatever in, don't even go through the CPU, just go straight from disk to GPU.
Yeah.
So I think that is new. I think today, Tommy, you cannot, if you just call open file, it's going to go to CPU standard memory, your main memory, and then you push it to GPU, even if you don't need to do any modification, you know, if you're just literally pushing it as is. Mm-hmm. So this new thing that they're building is designed for that case where if you're not doing any augmentation, if you've pre-processed everything and then saved it into, you know, a bunch of Parquet files, then you could just go straight from Parquet to GPU.
That's cool. Thank you.
I've been seeing various different things related to that. I was seeing that this is partially related. The PlayStation 5, one of its big advancements is they're saying that they can go the fastest directly from SSD to GPU that they've ever been able to. And there's some complex compression and all kinds of other stuff going there that's going to allow them to do faster compute on the gaming consoles now. And I believe that that's also becoming a piece of what NVIDIA is trying to do there, is they're trying to get the same experience on the computer.
Yeah, I think they're trying to compete with that.
Yeah. They've also, I mean, NVIDIA's bought several big companies and are trying to fill those networking and processor throughput gaps to try and make the best supercomputers possible. So I'm sure they're trying to address all of those optimizations that they can make. So moving on to the model design section. So the gist of this was they were showing there's lots of different things that you can experiment with. So you can experiment with the number of neurons, you can experiment with the number of filters, you can initialize in various different ways. You can add regularization, so you can add L1, L2, dropout, batch norm, all of these various different concepts. And it can have some meaningful effect on the performance of your network. So I guess we've looked at L1 and L2 a little bit in the previous chapters when we were looking at regularization of the linear models. So just touching on dropout briefly, there's various different flavors of dropout, but typically what you do is you just say, I want my dropout rate to be 0.2, for example, and then 20% of your neurons will essentially be shut off. And so they just won't have any linear contribution anymore. And then at the same time, when you're doing the backwards pass, that gradient won't be passed on the backward pass because they had no contribution. So then they're just essentially zeroed out. And the idea behind this is that you want all of your different pathways to be useful in some way. So if you randomly turn some of them off, then other pathways have to be used for similar knowledge potentially. And so there's various different ways of thinking about it. The way some people think about it is, since you're doing that sampling every single time, you're essentially taking many different network combinations and trying to all train them to do the same thing and work cohesively. Depending on who you talk to, they'll pose it in various different ways. So I just wanted to bring that up too. And dropout is very powerful. Almost every network that you see is going to use dropout in some form. And then they also introduced batch norm. One of the things we talked about in previous chapters is on the inputs, you want your inputs to be normalized between some range. You want it between -1 and 1 or 0 and 1 or some other constrained values. And so what people have found is you want that at the input because it gives you good mathematical properties when it's going through the activation functions and hopes they learn faster. But there's no guarantee that in later layers of the network, you have that same -1 to 1 or 0 to 1 or whatever your range is. So you can apply batch norm at later layers in order to keep that assumption and make it perform slightly better. And that's specifically useful in very deep networks where you might have it drift away from the mean and standard deviation that you're interested in. And so there's been a decent amount of research that has gone into batch norm. Some people believe one reason for why it works, some people believe other things. It's not exactly clear why it's so beneficial. I've also had negative experiences with it. So if you're ever playing with it, you might want to try turn it off, turn it on, see what happens, and just figure it out. Sometimes I've gotten erratic behavior on new evaluation data because it doesn't have the correct mean and standard deviation that is captured from the training data. But like I said, you just have to kind of experiment, see what happens, and then make a decision based off of that. Any questions on those two or other regularization techniques?
Hey, Ryan, I'm just going to make a quick plug. I would love to see a community talk on batch norm. It still seems a bit mysterious to me. So there's a couple papers that are mentioned in the book. I was thinking of looking at those, and I don't know if anybody here would be willing, but I'm talking to some different people about doing some additional topics. And for me personally, this would be helpful just because I kind of get it, but there does seem to be a lot of debate about it and interesting things, and so be nice to see some more stuff about it.
Hmm. So one of the last things they were talking about was, so we talked about you can add additional neurons, additional parameters, and then you can add regularization. And then the other thing is you can add additional depth. So let's say you started with 18 layers, now you go to some additional amount, 24 or 36, whatever you want. And so you can also get value with that potentially. So you have a deeper look at the data, you have more convolutions, more max pooling, you can end up with a slightly different result. And a lot of people have found that you do deeper networks and they tend to work better as long as you have enough data to justify the additional layers. And so one of the things with that is you have a very, very long network very deep network rather, you might not have gradients that can reach all the way back to the beginning in a useful way. And so what people have discovered is you can do what's called a skip connection, which kind of gives you a gap between layers that allows you to more easily pass the gradient along. So people have networks that are 151 layers deep, and in order to have a gradient that's useful all the way back in layer 1, they've done this trick where they essentially pass forward the input from previous layers, and so just directly skip 3 or 4 layers or something like that. And then you can say, okay, we at least know what the input was at the beginning, and so we can kind of address that even in deep layers, and make sure we have something that reaches all the way back to the beginning in a useful way. There's arguments for a lot of different networks. They were kind of mentioning too that everything becomes obsolete within a few months, basically, because people are constantly iterating with new network architectures and trying different things. For a long time, the ResNet residual network with those skip connections has been very popular and kind of the default, but people have come up with all kinds of different tricks. So if you really want to get the state of the art, then it's worth looking and seeing what other people have come up with. One of the popular ones now is EfficientNet, which is something that somewhat recently came out, and they basically did a neural architecture search to figure out what the best building blocks are. And so it doesn't necessarily rely on our formal knowledge of residual networks. It just was created from iterating and trying multiple different combinations. So just something to keep in mind. The residual networks are a good baseline, but if you ever want to go beyond that, there's other options that you can research as well. Any questions before we go to the code? So jumping over to the code, fairly similar to how we've always started. We've got all of our imports, matplotlib, numpy, collections, torch, and the various different submodules that we're interested in. We're working with the CFAR10 data set again. We've got the various different classes that are in CFAR10, and then we've got our same 2-tensor transformation and our normalized transformation, and so that makes up the data set that we're interested in. We've got the training set and we've got the validation set. And then we're doing the same thing we were in the previous chapter. We're only interested in the airplane and the bird class, and we know that that is 0 and 2, and they're remapping it to be 0 and 1. Here's our simple network from last time. So this is just a simple linear layer, tanh, linear layer, tanh, and so on. And so this isn't using the convolutions at all. This is just the one we learned about in the last chapter. And then this is looking at the, I believe that this is the total number of parameters, and this is the number of parameters of all of the different layers. I think it's maybe the actual weights and the bias for each of these. I'd have to double check on that though. So this is all old stuff. I'll skip over this. We look at a convolutional layer. So this is saying there's 3 input channels, there's 16 output channels, there's a kernel size of 3. And so if you just say a single number, if you just say 3, then it will just expand it out to the size that you're interested in. So we know it's a 2D convolution. So it understands that we mean a 3 by 3 and not just an actual 3. So you can also pass a tuple. And so if we wanted to, we could say 3 by 4. And so we could have 2 different kernel sizes. But since we just put 3, we know that it means just 3 by 3. And stride at default is 1. And so one of the things we were talking about is here's the actual size of the matrix that we're applying, and we're sliding this across the network. So if you ever want to inspect that, you can look at the weights and then you can look at the shape. And if you want to look at the actual weights, you can just remove this dot shape part and then you can see the raw matrix that is underlying.
Sorry, real quick question. Something I just thought about. Is there a way to get what the output would be for that layer, like after passing it through the conv layer, what the output would be shape? I mean, I'm just thinking because like, Keras automatically calculates it for you. I'm wondering, how do people normally build this? Do they just do the, math in their head or whatnot? Go ahead.
So that was one of the things that was mentioned earlier in the chapter. That quote that I was sharing is a lot of people do kind of just go by hand and they say, okay, I'm going to apply this operation. What's the output after this? What's the output after this? And you just kind of do it manually, just layer by layer, like you were saying. And so we can see that in this example that they're showing. So one of the things is we know that these images coming in are a certain dimension, and then we pass it through the convolutional layer, and we can see now that it's a slightly different dimension. That's what this border means, is we've lost 2 pixels. Does that make sense? And so the way that you do that is we've defined this conv layer, and then we've just said basically pass the image to the conv layer. And you can do this even if you've got a more complicated network. You can basically say, okay, what I do is I just put a bunch of print statements in my forward pass. So you apply the first step and you say, okay, what's the output shape? Okay, what's the input shape? What's the output shape? What's the input shape? And through all of the different layers, and you can just kind of track it along and say, okay, it's following the pattern that I expect, or it's going low on a certain dimension. I know that I can't do many more convolutions or else the image is going to disappear, basically. That's how I do it typically. There might be, I'm sure that you can derive it by hand, but it's much faster in practice to just apply it and just see what happens.
Cool, thank you.
Yeah. So this is the error they were talking about in the book. We have things slightly misshapen. We want it to be 512, but it's 64 by 8. And then they show that we can fix that by doing the view of it. And then beyond this, we're kind of doing the same stuff that we've done before. We're putting our data set inside of a data loader. We've got our training loop. This is kind of the same thing that we've looked at a few times. We're accumulating the loss just so we can print it out later and say, okay, the average loss is generally going down. We can see that it's improving over time. And so I can actually run this training loop. It's probably going to be a little bit slow because I'm just running it on the laptop though. But in general, we should see this number goes down over time, gets slightly better. So we can see it went from 0.57 to 0.33, and it'll just continue improving. So I'll cut that off early just so we can view the other code. So one of the things we talked about is this validate function. That'll be pretty common in your training loops. You want to add in some sort of validation because you can look at your training performance, but that's not really what you're typically interested in. You're interested in performance on unseen data. So you set aside some data and then you pass it into this validate function, and you apply your model in whatever realistic way that you want. So you're actually looking at the metric you care about, which might be separate from your loss actually. And so you do this validate function and you figure out, okay, on this set that I've set aside, how do I actually perform? And so you can run through this loop and figure out, okay, we get 80% accuracy, for example. This is showing the save process. This is showing the loading process. So we instantiate the network, we initialize it with random weights, and then we actually load in the trained weights at the end. And then this is showing how you push it to GPU.
Hey, Ryan.
Yeah.
I mean, just minor nitpick, but like that load command, you know, it's kind of like, I mean, really? You couldn't have figured out a way to load it in fewer than like 100 characters? Sorry, just
talking about this one.
Yes.
Yeah, that's just the reality of how they look. Yeah. Yeah. So this line is pretty common. This is what most people use when they push things to GPU. It's basically a check to say if there is a CUDA device available, assign it to the GPU. If there isn't, then push it to CPU. And so we can run mine and it'll say you don't have a GPU on this laptop. So just saying it's going to run these things on CPU. And then beyond that, most of these things, at the end of the chapter, they showed that layout of all of the different performances of the different networks that they tried. So the rest of this throughout it is kind of just defining new networks and then showing what's the performance of this one, what's the performance of that one, what if we add a layer, what if we add some regularization to our loop. And so eventually that builds into this visualization at the end of the chapter. That shows us here's the performance of our initial model with more width, with L2 regularization, with dropout, with additional depth, and so on. And so I wouldn't necessarily take these performance numbers as ground truth of what you would expect on all problems. It's just for this specific constrained CFAR 10 data set where we've even simplified it beyond that and we're just looking at airplane versus bird. So you can look at these and understand, oh, maybe this is a direction I should look in, but you shouldn't necessarily look at those performance numbers and say the solution is always more depth. So just something to be aware of. I don't know if we have time for this. It's not essentially complete, but I did want to at least give a preview of it. I've been talking about this for a while, but I wanted to actually do it this week, but I didn't find time for it. So one of the things that I've been interested in is what can a CNN actually do? And so I've laid out several different scenarios, just basically saying, okay, what are the various operations it can detect? What kind of things can it actually do? And so I've been looking at things like if you just put an image and it's just a white image and you just put two lines on it and you say, measure the distance between these two lines, can it accurately do that? Can it measure the area of this cube? Can it measure the distance between 2 points and various different things like that? And so I've been trying to build some basic examples showing that there's various different factors that are going on there. So the only one I've laid out so far is I've got this simple network that I've defined, very similar to the ones that we've been using in the examples. And then I'm creating this data set that's 128 by 128 images. And all it's doing is it picks a random horizontal point and then a random horizontal point below that at some point. And then the answer is the distance between those two. So if it's saying that the y coordinate is 35 and the second y coordinate is 55, then the answer is 20. And so I can show that very briefly. So looking at the output, I've got batches of 64, 3 channels. Doesn't necessarily need to be 3 channels, but I just did that to keep it compatibility with the pre-trained networks that assume red, green, blue. And then we can also look at the image and we can see, okay, it made 2 lines and they're 11 pixels apart. And then running this training process, we can see it starts pretty bad. It's 971, and that's mean squared error. So that's the square difference of the pixels. And we can see that it improves over time and eventually gets to something that's pretty good, but it never perfectly learns this task. And there's various different reasons that you can explain why it's impossible for it to learn the exact distance between these pixels. So once I figure that, I'll do a more detailed write-up on all of this. But if anyone wants extra credit, do you have a guess why it can't achieve a perfect solution?
Haven't trained it long enough.
More data.
So it has actually unlimited data because I'm just generating it on the fly.
Yeah.
So it's seeing new samples every single time, and it's just learning more and more and more.
I mean, you've got noise in there, right?
No, not necessarily. There's
No? Okay.
noise. Yeah.
Is it because we lose some information over the convolutions, or it's not as precise?
So let's look at the definition of the model to understand what's going on here. So we've got some convolutions, we've got some X pooling, we've got some convolutions, and then we've got a fully connected layer to map it down to the one single thing. And so we're sending it to a float, we're doing convolutions, and then we're doing max pooling, and then we're doing convolutions, and we're doing max pooling. So looking at the details of the max pooling, what is the max pooling actually doing? It's looking at 2x2 blocks, and it's taking the max out of those. So every time you do the max pooling, you're actually losing precision, because was it this pixel over here that was lit up, or was it this pixel over here that was lit up? You do the max pooling, all of a sudden you've lost that precision. You don't know which one it actually was. So it's physically impossible for the network to converge beyond a certain point, given how much you do max pooling. There's a certain level of pixels that you just cannot tell, because the max pooling actually loses that precision for you.
It's like a rounding error, right?
Mm-hmm. Yeah. So this will level off at probably around 80, and it just cannot go beyond that as long as you train this network. And there's nothing, as long as you have max pooling in there, it's physically impossible for it to do. And so this is kind of why I'm actually setting these out, because I think there's a lot of interesting things that are actually happening here that are kind of non-obvious unless you actually do these fundamental experiments and understand what is actually happening with these operations.
Does average pooling get closer than max pooling?
I haven't tried, but we could plug it in. I would think that it would be the same. I'm not sure though.
I was kind of thinking the same question. I think average pooling might do slightly better.
Yeah, we can try that.
So with your images that you're generating, they're always going to be horizontal lines some distance apart. Is that correct?
Yeah. Yeah, that's correct. I just wanted to lay out a very simple scenario because you would think like, oh, this network is the same network that can figure out what a dog and an airplane and a cat is, but it can't measure the distance between these two lines. And so it's kind of interesting to think about that a little bit. What does that actually mean? And it's actually somewhat material to the stuff that I'm working on the lift competition, because something that's important when you're doing self-driving stuff is you're trying to understand what is the distance between these two vehicles. So maybe that is actually material in some way, that convolutions and max pooling might actually not be a good fit for that scenario.
Would it help if we use some specific kernel, like for horizontal edge detection, because we have all the lines which are horizontal?
Potentially, yeah. There's probably some alternate layout that would be more successful. So one of the other things that I wanted to lay out is your network actually only has so much range. So if you apply a 3x3 convolution and that's all that it has, then it can only tell things that are 3 pixels apart. So another network that I laid out, basically, it does not have the range to tell certain distances when they're beyond a certain length. So if there's one at coordinate 1 and one at coordinate 127, it cannot reach. It does not have the ability to reach all the way across the network if you don't lay it out correctly. So that's just another scenario that is interesting to look at. There's a lot of different ways that you can cut it and find kind of weird little anomalies. Maybe someday we can have a little hack session and we can just lay out a bunch of different tests and see what happens, because I think it's kind of interesting fundamental research.
Average pooling seems to be learning slower.
Yeah.
I don't know if it's going to converge differently, but it seems to be getting there slower.
Yeah. So if anyone also wants to propose little experiments for me to add in, I'm open to that too, because I'm trying to just lay out a bunch of different tests that I can apply. And it's, I mean, you look at the code that I did to create this data set to make this test is like 8 lines of code total, 6 lines of code maybe. So kind of just a fun toy problem.
I'm curious about number of filters. How does it influence the conversions? I mean, I understand that memory will swell up, but how are they exactly generated, by the way? Technically, how it is done?
How are the features generated?
How filters, convolutional filters, how they're generated.
Mm-hmm. So that's
because you had an example with numbers, -2, -1, 0, 1, and 2. So it's 5 numbers. 5 numbers for 3x3 matrix. So it is combinations is 5 to 5th. I just computed it. It's about 2 millions.
Mm-hmm. Yeah.
So of course, many of them are repeating and redundant. But in general, how they're generated.
Mm-hmm.
If it is not completely random, it shouldn't be completely random, because a filter with all ones is the same as with all negative ones.
Mm-hmm. One of the things that I am interested in looking at is we have all these layers, and we can view what these layers are actually outputting in order to solve this problem of measuring the distance. And it might be interesting to say, okay, what is the actual sequence of operations it's going through to figure out what the distance is between these two?
Well, I guess one of the things I'm thinking about right now is this seems like a convolutional neural network isn't the right approach. I mean, so are we doing this just to test how well we can get a convolutional neural network to predict a distance?
Yeah, so I'm trying to lay out a series of tests for a CNN and say, what can it actually do? And so,
what are the limitations of a convolutional neural net? How far can you take it? Yeah, that's very interesting.
Maybe a little bit of a hack, but maybe you can just draw a bounding box between those lines and see what the coordinates are that it finds between those lines.
Yeah. So one of the other tests that is interesting is taking, so we can see the loss goes down over the patches over time. So one of the other tests that I think is interesting is I've taken the pre-trained ResNet 18, and you would think, oh, this is this amazing model. Let's see if it can converge to learn that simple measuring task. And it actually does worse than the other system. And so we have to kind of inspect it and say, why is that the case? Why is it so much worse? It doesn't even really converge to learn this stuff.
Another question I've had is, so if you have a dog and a cat detector, if you separate those out to just a single dog detector and a single cat detector, will those perform better than a dog and cat detector, together? And I guess it's, all of the training and the weights and everything, if they're all merged together and you have a dog and a cat, technically you have the possibility of making an error, more chances. I would think a single dog detector would be a better, better accuracy.
But when you have a model, usually you compare with something. You should have one class and another against which you compare. If you compare a dog with a house, I don't think it would be good at distinguishing a dog and a cat.
Well, that would suggest that you need to tailor your training data based on some criteria, I guess, yeah. But the CFAR has, everything, and it seems to work okay, so yeah.
Ted, you're on mute.
Do they have cats too?
Sorry. I was saying, even if we generalize it more so that we have more animals, so let's say it's, dog or cat or, I don't know what's a good choice, deer, okay? You could have the dog versus deer classifier, the dog versus cat classifier, the cat versus deer, and whatnot. I understood your comments. My intuition is that a single classifier that decides between the three would do better than the, I don't know what it is, 3 different classifiers that would pairwise compare them, and then if you had the 3 of them vote.
Yeah.
If nothing else, I mean, I think there's 2 intuitions. One is just in general, this idea, Ryan, you've coached me on this many times, of the shared information, right? But even if you don't think of it that way, just the fact that you would have 50% more training data in your 3-way model.
Right.
So if nothing else, if you've got 10,000 dogs, 10,000 cats, they're only going to get 20,000 examples on each of the pairwise classifiers, but the other guy is going to get, I don't remember what numbers I said, but it's going to get, that extra bit more. But then if you stumble upon anything that's good from, telling dogs from deer, that may also be useful for telling cats from deer.
Because one strategy is you can look, like if we're looking for medical, we're looking for a particular piece of anatomy, you make a custom detector just for that. And if you detect that, then drop into a second neural net that would detect substructures based only on that. So there's all sorts of pairing and combinations you can do here.
Yeah. I mean, aside from just the logistical nightmare it would be if you're trying to detect 100 different things to have
Yeah.
all those, you know, whatever,
Yeah.
5,000 pairwise, you know, combinations. But even if that were not an obstacle, I don't actually think you'd get better performance.
Yeah. The fact that it even works is just mind-boggling. When you look at this, you're going, how is this possible? Yeah.
I figured out something stupid I did. The reason the ResNet was not converging was I never passed the ResNet to the optimizer. So it was continuing to stay just random the entire time. So that is the explanation there. I was wondering why that was the case.
Were you using pre-trained or not pre-trained weights?
I was using it pre-trained.
Yeah. Okay.
Yeah, but it was getting zero training signal at all. So now let me try this.
Okay. So while you're starting that training, you know, another comment I wanted to make is I definitely spent more time on this chapter than the previous chapters. I had to look at the code listings, you know, spend a few minutes on some of the code listings. At least for me, I am not, I was sharing with some people earlier, you know, I didn't grow up on object-oriented and I'm not the strongest Python coder, so I don't know Python in and out, backwards and forwards. So I had to kind of look at the code a little bit. But I did want to comment that, so there's a little bit of code that I had to look at in terms of, oh, so you define the actual units that are in your layers, and then in your forward pass, you say, I'm going to basically compose these functions where I'm going to call these things in this particular order, you know. Just imagine how much harder your life would be if you had to manually write the code to do the back propagation. Right? Because I mean, that's how things were up until, I don't know, what, a couple of years ago? A few years ago, maybe? So I think it's pretty amazing that you just simply say, if I have 10 layers, I'm just going to call, you know, layer 1 and then, you know, layer 2, layer 3, and just composite all the function calls. And then you can just basically say, you know, optimizer, take a step. And you don't have to write any code. That's pretty amazing.
So interesting. So this ends up getting a significantly better value and it converges a lot faster. And that's kind of expected because it's the pre-trained ResNet. But then also if we look at it, it only has a single max pooling layer and it has a kernel size of 3 and a stride of 2. So it's a slightly smaller reduction, and then the rest is all convolutions. So I think that is actually a decent explanation as to why it's able to get a significantly better value.
So you added dense layers to the top of the ResNet?
Yeah, so I added a single layer that takes its normal reduction from 512 down to just 1. But other than that, I didn't touch the rest of the ResNet.
Because I'm wondering, Ryan, it seems to me that you actually could solve this problem with the dense layer without the CNN at all.
So one of the other questions that I was going to look into was, can you expand this to a larger image? So right now it's 128 by 128. Could we scale it up to 256 by 256? And that still understands the concept of I need to measure the distance between these two lines. With the dense network, that completely would not work. But with the CNN, it might if you train it properly.
I seem to recall there was, you know, a lot of these companies, these startups that are doing this for real work, you know, that do this for a living to come up with the smallest neural network possible. I seem to recall there was a tool that was an iterator tool that basically did all permutations of depths and all of these variations on these massive computers, and they just look at the plots and basically pick the best one out of all of this stuff. So, yeah.
Yeah.
The other way is to really understand how it works. But yeah.
Hey guys, so it's the top of the hour, so I wanted to do just a little bit of administrative stuff. So just briefly, next week we're going to move on, but chapter 9 and chapter 10 are both short chapters, and there's not a lot of material there. So chapter 9 is introducing a problem that we're going to solve in the next 5-ish chapters. So it's detecting tumors, cancerous tumors in these CT scans. And so there's absolutely no machine learning whatsoever in chapter 9. It's just talking about what is cancer, what is a CAT scan, that kind of stuff. And then chapter 10 is prepping our data set. So it's not actually getting into the neural network stuff at all. So, so what we decided is we're going to combine chapters 9 and 10 for next week. And then if you're on Meetup, I actually created a little bit of an image for it, so it looks a little bit different. But just so you know, it's in case you're worried that something happened, whatever. Nothing's changed. We're continuing with the book. But I am planning to do a very brief recap of chapters 1 through 8 at the beginning of next week. And so I am trying to let some of the people I know in my network that if they were thinking about possibly joining, but they didn't want to join in the middle of a book, that next week is actually a really good time for people to jump in. Obviously, if you're like completely new to machine learning and have never seen a neural network before, then that might be a little bit steep. But basically, we'll just go over, quickly. Here's the training loop. Here's the CNN, and then we'll start talking about the the actual solution that we get in the next 5 chapters in the book. So just kind of wanted to let people know in case people had any questions about whether something was changed or not. I don't know. That's all I can think of. Anything else, Ryan?
No, I think that's it. So, short 15-minute break. We'll be back at 2:15 for anyone who wants some project collaboration time. I've got various things I'm going to share about the projects I've been working on. If anyone else wants to discuss and chat about stuff they've been working on, feel free to join us. But if not, see you next week, hopefully.
All right, cool. Thanks.
Thanks, Ryan. Thanks, Ted. Bye, everybody.